Yeah, so thank you everybody for giving me the opportunity to come here and share this work with you today. This is some work that was led by Kyle Deeds. Kyle's a student at the University of Washington, working under Dan Suchu. And Kyle, his background is a little bit more in like databases and cardinality estimation. So Kyle does like theoretical work on cardinality estimation. Kyle reached out to me a couple years ago after he read a paper about like asymptotic auto-scheduling that was a PLDI 22. And he said, hey, this database stuff is something that we should really look into for sparse tensors. And so now we will talk a little bit about the system that Kyle built as a result. So this is my slide. I'm obsessed with array programming. I start every talk with a slide about how much array programming has changed our world, and it kind of changes how we think about programming with collections of data. We're all using Numpy and Tensorflow to write machine learning models and scientific simulations and all of this stuff, and it makes it easy to do. A lot of these systems are optimized for dense tensors, and one of the reasons for that is, this is sort of, Rohan mentioned the kind of enumerative slide that we all have. I'll take a different take on this slide, but we have to fuse our operations together with sparse computing, which means that each operation needs to be treated separately. We also have this issue that we're going to do many different sparse formats, right? We have different kinds of structures beyond sparsity. Maybe there's blocks, or you might do things that are like not quite sparse, like run length encoding or symmetry. And then, of course, we have many different ways that we'd like to execute this kernel, different schedules. So you could do different traversal orders, or run it on a GPU, or here we want to do some blocking and tiling. So, of course, we know that this is too many kernels to implement by hand, and we need to use a compiler. I would argue that in this room, a lot of the solutions that we've generated have solved these four horsemen of this apocalypse. So we have collectives. We saw in the previous talk where we have a lot of really interesting interfaces to make it easy to program with these tensor compilers and specify particular kernels. We also have these hierarchical descriptions of data structures, right? Whether using hash tables or lists, we can describe a sparse tensor as a tree, and we have a lot of compilers that are really good at mapping these tree-like structures to efficient code. Of course, we can change the kind of data structure we use at every level. So there's a lot of parameterization going on. We can adapt this concept to handle different kinds of structure that we might see. And then, of course, we have scheduling commands, right? This was a really big innovation in performance engineering because it makes it a little easier to write transformations on the code without having to do all of the heavy lifting yourself. And it allows you to make sure that the idea is that these commands will reorganize the code after you've already said what you want to kind of tell you how to compute it. And of course, you might also think of this in terms of kind of describing the data flow at a high level, right? And then you can adapt that to the structure. This is too many options. This is a really big slide. This is a lot of custom, very specialized knobs and bells and whistles that people who are programming these things have to actually learn in order to use the tensor compilers effectively. And so the situation that we get, right, is that we have our domain expert. We want to do some Python on our data, and the structured code is really complex. We have all of these choices. And so we ask a performance engineer to do it, right? And now the performance engineer is writing the schedule. And so at some level, these scheduling languages are a really great marketing innovation to talk about how to say that the interface is really here, but the schedule is going to be down here. And so in some ways, I would argue that if the last human in the loop is at the level of the scheduling interface, then really this is the interface, right, and not the high level thing. And so I think really in order, so another caveat here that makes everything worse, right, is that the performance also depends on the sparsity pattern. So we need to draw a little line here, which means that now we're asking our performance engineer to do different specializations for different data sets, just adding on to the problem. So if we really want to claim that our interfaces are at this high level, then I think that we should, everything beneath the interface should be automatic. So to give an example of why the performance depends on the sparsity pattern of the inputs, consider a sparse matrix vector multiply here, where we're multiplying with this sparse vector. You can do this two ways. If you do this in a row major order, you see that we kind of have to traverse both of these lists, and when the two lists don't share a non-zero at the same location, that traversal is kind of wasted. We're checking if the other one has an element, but we're not actually doing them all. And so here you can see the row major traversal is doing a lot of checking and not very much multiplying. One thing we like about row major traversals, though, is that it's output stationary, which can be a big deal if you're parallelizing or something like that. So the column major traversal is like asymptotically better. We can check based on the vector x whether we actually need to traverse the column at all, which is a huge improvement. So here we see the difference between the two. So as we're making our decisions about cost modeling, it really, what we need to do is come up with a way to model the cost of the actual matrix as it relates to the computation. So we'll take an example of like a matrix multiply with two sparse matrices. Here's our example loop order. So this is the Gustafson's algorithm for matrix multiply. And here's our two example tensors. They're in a tree. A is a very complicated tree, and B is a very simple one. But we're not going to worry too much about the structure of B here. So here, in our loop over I, we're going to be looping over these edges. And then in our loop over K, we're aligning these two vectors, right? This is that same problem we just saw in the sparse matrix, sparse vector case. So here we see that the two values of K are shared, and so we should traverse this element J. Here we see, the first entry in the row of A is 2, and so then, of course, they have that shared entry, and we need to do the multiplication. But in this other case, if it's 3, they don't match, and so we don't do them all. And so if we were to add a cost, we might say that this I loop is going to iterate once for every non-zero row of A. The K loop iterates once for every entry of A. And then the J loop is going to iterate once for every non-zero in this three-dimensional object that I've sketched here. So this is a really simple way to talk about the costs of this algorithm. And so we could actually compute these things and figure out what the cost would be. Of course, actually running the algorithm is expensive, and we need to do a lot of different, as I said before, there's this combinatorial explosion of all these different choices we need to make, and so we need to be able to model the cost efficiently. So this is where the database literature starts coming in. We can draw an analogy to cardinality estimation. So cardinality estimation is just estimating the size of a join in a database world. But there's a couple differences. One is that dimensions are finite domains, right? So in the database world, we have these infinite attribute domains. Here they're finite. Another is that aggregates are really common in the sparsity world. This is something Amir was pointing out. And selections are uncommon. And so we chose to use degree sequence bounds. This is also like a bound that I think Kyle is very fond of. And so the idea here is that it's a distribution over the occupancy of the matrix. So you're essentially asking, how many rows are there of length 1? How many rows are there with 2 non-zeros in them? How many rows with 3 non-zeros? And you can use this histogram as kind of like a way to estimate the sparsity of certain outputs. In particular, this gives us an upper bound on certain sparsities, which is useful to us because it's safe. So we don't make decisions that are, catastrophic. But you might choose other cardinality estimation. There's many different estimators that you can choose. So how do we build this into an optimizer? We have, you can kind of think of autoschedulers as having you need a search space, you need a cost function, and then you need a search strategy, right? Now we're in the search strategy part of this. So we have our input program, it's in our Numpy. We'll pass this to a logical optimizer, which results in this logical plan. At this stage, we're just choosing which kernels should be fused together and which ones happen separately. Then we pass it through a physical optimizer. This is making decisions about what the loop ordering should be, what formats we want to use for intermediates or for the outputs. And then we pass it to a sparse tensor compiler. And of course, the sparsity estimator is based on the inputs, the sparsity estimator is going to use the inputs to inform these two stages of optimization. I'm sorry, is that me? Oh, okay. I'm going to keep going. Anyways. You can see this talk about, I can talk more about Finch. We have a paper at OOPSLA, so if you want to see more about that, it's a talk I've given many times already, so you can go to Singapore to see that, and we'll skip that for now. Let's talk about Galley's logical optimizer. So the problem is that optimizing join ordering and aggregation simultaneously is a huge search space, right? It's hard to choose all these fusion optimizations by just some enumerative search. So our solution here is the same solution as in databases. We'll use variable elimination. So the idea is that an elimination is we will pick a particular index that's in the sum, and then we'll sum over that index, and that leads to an intermediate tensor. So the idea is that if you choose the order in which you want to do these sums, that's the main fusion decision that you're making about which tensors need to be processed together. And so focusing solely on this index by index approach really reduces the search space. And of course we'll do, we still have an n factorial number of orders, and so we can do a little bit of dynamic programming and stuff like that to reduce it. But the key idea is that this elimination order implies a fusion plan. So to give a little example of what this might look like, we have our classic matrix chain multiplication, and we can represent this with a little expression tree. So here's our summation over j and k, and then we're going to do the pointwise mole over all of these. So this pointwise mole is you can think of it conceptually as producing a four-dimensional object here, because there's four distinct indices. But if we do a j-k ordering where we sum j first, we see that j is touching a and b, but not c, and so a and b are involved in this elimination. And then k is involved in the subsequent elimination. That leads to a plan like this. Of course, you could do the other way, and it would lead to a different plan. This leads to a little bit of a question, because I've been moving these summations around, and not everything is summation. We just had this excellent talk from Hamir and Mateus about all of the different array API operations that we want to support with a system like this. So we get really specific about which algebraic properties we're using to push aggregates down the tree. So in particular, we need to use distributivity to do some of this, and commutativity as well. So certain algebraic properties might restrict the elimination orders that are available to us as we do this search. So we're kind of pushing the aggregations down as much as we can, subject to the algebraic properties that we're working with. Then, of course, we hit a physical optimizer, and these sort of concerns may be more familiar, where we're talking about optimizing a loop order. The general idea is that you want to lift the filters higher in the loop nest, but we can of course use a similar dynamic programming over the orders, and then of course we have to pick formats. And the nice thing about using sparsity estimation is that we can use it again here to estimate what the actual cost would be in any given format that we're choosing. So we choose among 4 different level formats that we found were sufficient to cover most of the use cases. And they have a couple different properties. So the bitmap and the dense one store a full dense representation. The bitmap is unique in that it allows you to do a traversal over just the sparse elements, where a dense representation wouldn't even allow you to do that. And then, of course, we have hash tables and sorted lists, depending on whether or not we need random access in the case that we really truly want to have a format that is O of n and z rather than O of n. And then, of course, we have the issue of intersection algorithms. Because Kyle is from the database world, we'll take a database-inspired approach here, and we'll do the iterate lookup strategy. We have a sparsity estimator, and so it can tell us whichever one is smaller. So in this case, this is actually the bad choice. We'd probably want to iterate over B first and look up into A. But the idea is that you can just pick one of them as the leader and then look up into the follower. So we have a little bit of results here. We use, so we're focusing on subgraph counting for our experiment. The idea here is that we're going to count the occurrences of a graph within another graph. And it's equivalent to taking a product of the graph matrix with itself enough times to represent the small query object. So this is where we get triangle counting is really just a matmul of 3 matrices. If you want to count something other than triangles, then it looks like a different matrix chain multiplication where the indices are shared in various ways. And so there's a couple standard data sets and queries based on this, but we think it's a good test of an autoscheduler because it really has like a lot of variance in the kind of kernels that we're testing against. And we see that we're competitive with state-of-the-art database optimizers like DuckDB. Of course, one interesting thing that we can see in some of these plots is, as you might also ask what the execution time would be if we used a different backend. So how much of this is like the execution engine, or like Finch versus DuckDB's vectorized executor, and how much of this is actually like the sparse compiler point of this. And we see in certain data sets that using a sparse compiler is actually helping us quite a bit, whereas in other data sets the difference is less so. I'm going to skip this one. Anyways, we also, for a more familiar comparison, we did a little bit of matrix chain multiplication on a pathological example with PyTorch's sparse matrix multiply. And so in this case, C is super sparse, but A and B are more dense. And you can see that as C gets sparser, the performance of PyTorch is staying the same. It's doing the same, multiplying the 2 dense matrices first, and then, so it has the wrong order. Interestingly, if you swap the order, you would think that PyTorch would start to do better, and it does, but it doesn't quite match the performance. I believe this is because it doesn't have a doubly compressed format that it's choosing to use. So at some point, we realized that indeed we should also start compressing the rows in addition to the columns, like the DCSR. So that's our hypothesis for this one. And then this is an example where we do a matrix chain multiplication, where I believe that this is related to whether you really need to materialize anything at all in this. Yeah, in conclusion, I think that sparse autoscheduling is both necessary and achievable. We've written some great tensor compilers, and I think we can also write code that knows how to drive them. Existing tensor compilers have a lot of complex bells and whistles that make it hard for the average user to use them without knowing how they really work. But an autoscheduler like Galley can get us to this usability that I think we're all hoping for. There's a little archive QR code. Thank you for your time.